Marhaba. Okay, this session is about prime numbers. So remember, we are in the chapter of number theory, and number theory is the study of integers. And today we want to talk about very special integers called the prime numbers. Okay, so let's first define what is a prime number. So this is a definition. Okay, an integer. Okay, let me first say what is a prime number. So a prime number is a positive integer bigger than 1 which has no divisors, has no positive divisors other than 1 and itself. Okay, so an integer, an integer p which is strictly bigger than 1 is prime. We call this integer prime if the only positive divisors of p are 1 and p itself. Okay, remember we defined what is a divisor, right? A divisor, so k is a divisor of, okay, let me say this, so k is a divisor of p if k divides p. Okay, which means if there exists some integer L such that p is equal to k times L. Remember, k divides p means we can reach p by taking, say, L steps, each of length k. Okay, so the only divisors of a prime are 1 and itself. And these numbers are very special in number theory because we will see from what is called the fundamental theorem of arithmetic that we can write every integer as the product of such numbers. So they play the role of the building blocks of integers. They are like atoms in chemistry. Every molecule is made from atoms, and here every integer is made from prime numbers. Okay, now if n is not prime, if an integer n is not prime, we say n is a composite number. We say n is composite. Okay, let's break it down. What does it mean to be not prime? It means n has a divisor which is not 1 or itself. So n is composite, so i.e. there exists an integer k such that k is strictly bigger than 1 and strictly less than n, where k divides n. Okay, moreover, so what does it mean that k divides n? It means that n is equal to k times L. Okay, so, and in this case L should also be between 1 and n. Okay, so also we can say there are k and L where both k and L are strictly between n and 1 such that n is equal to k times L. Okay, so here k and L are strictly between 1 and n. So let's take some examples of prime numbers. So here are, let's start listing prime numbers. Okay, so the first prime number, a prime number by definition should be bigger than 1. Look at 2. 2 is prime because the only positive divisors of 2 are 1 and 2. And then 3 is prime as well. 5 is prime. 6 is not because it's divisible by 2 and 2 is between 1 and 6. Okay, 7 is prime. 8 is not. No even number is prime other than 2 because any even number is divisible by 2. Okay, 9 is not as well. Then we have 11, we have 13, we have 17, 19, 23, okay, 29, 31, and so on. We don't know when this list stops. Okay, so these are examples of prime numbers. Now let's have an example of a composite number. Okay, so composite number are all the numbers which are not here. Okay, positive integers if you want. For example, choose 15. Why 15 is not prime? Because it's equal to 3 times 5, which means that 3, so this means that 3 divides 15. 3 is a divisor, and 3 is not 1, and 3 is not 15. So this means that we found a divisor of 15 which is neither 1 nor itself, and this violates the definition of a prime. So 15 is not a prime, it's a composite number. Okay, now let us state what is the fundamental theorem of arithmetic. Okay, the fundamental, we already mentioned it, but let's officially state it. The fundamental theorem of arithmetic, again, intuitively speaking, it says that prime numbers are the atoms of the integers. So what does it say? Every integer n greater than 1 is, or can be written uniquely, as product of primes. And here product of primes include the case where the number is a prime itself. Okay, product of primes. We've seen this theorem before in the session about strong induction. So we proved this using a strong induction, but we didn't prove the uniqueness part. And what is the uniqueness part is that, for example, let's take 24. Then 24 is an integer bigger than 1, so it must be the product of some primes, so it's 2 times 3. Okay, maybe I want... so it's 2 times 2 times 2 times 3, right? 2 times 2 is 4, times 2, 8, times 3, it's 24. So here we see that 24 is made up of 3 prime numbers of 2 and 1 prime number of 3. Okay, so these are the building blocks of the number 24. And the uniqueness says that if we say arrange the product of primes in an increasing order, then any product of primes of 24 is this one. Okay, so you can't find any other primes which when you multiply together you get 24. For example, you can't say these are the only primes, so 3 2's and 1 3 are the only primes whose product is 24. You can't find any others, okay? So for example, let's take more examples. Take 33, it's the product of primes, it's 3 times 11. So the only 2 primes whose product is 33 is 3 and 11. You can't find others. Okay, what else we have? For example, 5 is a product of prime because 5 itself is a prime. So here 5 is equal to 5, say. 35 is equal to 3 times 5. 40 is equal to 2 times 2 times 2 times 5, right? 3 2's and 5, and so on. So choose an integer and try to decompose it into prime numbers. Okay, for example, look at 1024. This is, you can see that this is 2 to the power 10, okay, which means it is composed of 10 2's. Okay, what else? Look at the number 100. What is the prime decomposition of 100? You have 2 times 2, which is 4, times 5, it's 20, times 5, it's 100. So 2 2's and 2 5's made up the number 100. And these are the only primes which make up 100. Okay, so this is about the fundamental theorem. Okay, so we proved that every number is the product of primes by strong induction. It remains in this number theory chapter to show that this product is unique. Okay, we will still need to prove this. Okay, let's have a very nice theorem about prime numbers or composite numbers if you want here. So theorem, if n is a composite number, okay, then suppose you know that a number is composite, then we know that it has divisors other than 1 and n itself, but this theorem says more. Then there is a prime, one of the divisors is a prime, of course. Then there is a prime, say p, which is less than or equal to the square root of n, which is a divisor of n. So such that p divides n. Okay, and this is very nice theorem. You will see why if you compute its contrapositive. But first let's prove it. Okay, so prove. So again we will use direct proof. Suppose n is composite. So suppose n is composite, then what does it mean? It's composite. Then there are integers, say let's call them integers, let's call them AB, and these AB are strictly less than n and strictly bigger than 1, right? N has divisors which are not 1 and are not n, okay, such that n is equal to a times b. Now we claim that one of a or b, either a or b, is less than or equal to square root of n. So we want to show this by contradiction. So for the sake of contradiction, okay, suppose that both, look, we want to show that either a or b is less than or equal to square root of n. So for contradiction, suppose that both are strictly bigger than square root of n. So suppose that a is strictly bigger than square root of n and b is strictly bigger than square root of n. Both are strictly bigger than square root of n. Then multiply the left hand side here. So then a times b is strictly bigger than square root of n times square root of n. Okay, but what's a times b? Look from here, a times b is n. Okay, strictly bigger than, what's square root of n times square root of n? It is n, and we obtained that n is strictly bigger than itself, and this is a contradiction. Okay, so which means our assumption that both are bigger than square root of n cannot happen. It means that this is false. So remember, this is it's p and q. This is a statement of the form of a conjunction. Not this means, by De Morgan's law, not this or not this, right? So it means thus either a is less than or equal to square root of n, or b is less than or equal to square root of n. Okay, one of them must be true, either this or that. Let's say without loss of generality that a is, so without loss of generality, suppose a is less than or equal to square root of n. Now, by the fundamental theorem of arithmetic, what do we know about a? A is an integer. A is a product of primes. So a is equal to p1, p2, sorry, okay, up to pk. I don't know, it is the product of some primes. Choose any one of them. So say, so by the fundamental of theorem of arithmetic, some prime, any one of them, let's call it p, divides a, right? Because look, let's say p1 is a prime, then look, all of this is an integer. Let's call it r. The product from p2 up to pk is r. Then this means that a is equal to p1 times r. But this means, by definition of divisibility, that p1 divides a, right? Because what does it mean that p1 divides a? It means there is an integer, say r in this case, such that p times r is a. So we know that some prime p divides a, but okay, any divisor of a, and so this, since p is a divisor of a, then p is less than or equal to a. But a is less than or equal to square root of n. Okay, so here we found a number which divides a and it's less than or equal to square root of n. Now what do we want to show? That look, from here, what do you know about a? N is equal to n is equal to a times b. This means that a divides n, right? Okay, so what do we have here? That we found the prime which divides a, and from above we know that a divides n. Remember, we proved one of the properties of divisibility, which is called transitivity, that if p divides a and a divides n, okay, then, so since p divides a and p divides n, we have that p divides n. So p divides n and p is a prime, and since p is less than or equal to square root of n. Okay, so this finishes the proof. We found a prime p, okay, which divides n, and this prime is less than or equal to the square root of n, which proves the statement of the theorem. Okay, so if n is composite, then there must be a divisor which is prime and less than or equal to square root of n. Okay, why this is very useful? Let's write down the contrapositive of this theorem. Okay, so what is the contrapositive? The contrapositive will be, so corollary. So this corollary will be a nice algorithm or a nice test to see what if a number is prime or not. So let n be an integer, say positive integer, then if for all the numbers k from, not even all numbers, if for all prime numbers, if for all prime p, where p starts from 2 and up to square root of n, okay, we have, okay, so look at all the prime numbers between 2 and square root of n. If this prime does not divide n, then n is a prime number. This is the contrapositive of the above. So we proved that if n is not prime, which means if it's composite, then one of the divisors will be prime and between and less than or equal to square root of n. So the contrapositive says if no prime between 2 and square root of n divides n, then it must be not composite, which is prime. Sorry, not composite, which is prime. Okay, so let's use this corollary. For example, look at this example. Okay, show that 101 is prime. So let's look at square root of 101. The square root of 101 is less than or equal to 10 and strictly less than 11. So all what we want to check, if the primes between 2 and 10, what are the primes? So let p be 2 or 3 or 5 or 7. These are the only primes which are less than or equal to the square root of 101, which is 10. Okay, I mean the floor, if you want. Okay, the floor of this number. Now let's see. 2 does not divide 101. 101 is not even. 3 does not divide 101 as well. You can check all of this. 5 does not divide 101, and finally 7 does not divide 101. Okay, since no prime between 2 and square root of 101 divides 101, we can conclude by our work above that 101 is a prime number. prime number. So if you want to program an algorithm using C++, say to take an integer as an input and check if it's prime or not, you only need to check if all the primes between 2 and the square root of the input divides, if any of them divides the number, then it's not prime. If no one, like in this case, so no one of these divided the 101, then you can conclude that the number is indeed a prime number.